Okay, hello, everybody out there. Can you hear me? Welcome to our tutorial. If you can hear me, can you put something in the chat to make sure I'm coming in loud and clear? Hello, Menglu. How are you? Um, it is the deeper understanding tutorial, and we have a grand total of 6 people here. So I've had a few requests for certain questions, but let me know what you want to discuss today. I thought we could do a little bit of calculus and a little bit of algebra. So let me know what's going on in the either in the chat, or you've got your microphone. You can turn it on or turn your um, camera on. Just there aren't a lot of people here, so we can just sort of be pretty relaxed. Okay. Um, hope the I hope the lab test one went okay. Um, Hopefully there were no surprises. So why don't we do some calculus first, and then we can move on to some algebra. So I thought we could look at this one, number 6. This is chapter 5, at the end of chapter 5. And then I thought we could do one of these error bounds questions, because I think this is important, because in lectures, I don't think I did an example involving error bounds. So I might just do like this one or something like that. Okay. All right. So let's start at number 6. And I'll prove half of this, right? So I'll prove one half and you can prove the other half. Okay, so let's prove this inequality first, and then I'll leave the other inequality for you to prove. Okay, all right. So if I open up GeoGebra and I put in what are the functions? Square root 1 plus x and 1 plus x on 2. So let me go over to GeoGebra. Okay, so I'm over here. And if I put those two in, you can see that for x bigger than 0, the blue curve appears to lie below the orange curve. Okay, so it kind of looks like this is true, okay, at least from a picture. All right, we can zoom in there. I'm not sure if the blue line goes above there, but we're only interested in the case when x is positive. So let's see how we can prove this using just our regular inequalities. And I think the way they want you to do it is to use the mean value theorem. Okay, so let's prove half of it, and then I'll leave the other half for you to do. Okay, so show that this inequality holds for all positive x. Okay, so with these kinds of problems, there's usually a standard algorithm or a standard strategy that you employ. Okay, so what I'm going to do, I'm going to rearrange this, and I'm going to introduce a function which is just this on the other side, and you want to show that this is positive. So if we can show that this function is positive for all positive x, then that's equivalent to showing this. Okay. All right. So usually the next step in this problem is to define a new function. With different variables. Okay. So it's probably the same function, but just different variables. Okay, so x is positive here. We've just changed the x's to t's, and we're going to look at how we can apply the mean value theorem on this interval. Okay, so our f is continuous. So for every positive x, this function is definitely continuous. And so by the MVT, there is at least one point C such that, okay, so by the mean value theorem, there is at least one point C, but strictly between 0 and x, such that this is true. Okay, so we simplify the right-hand side and we'll form an inequality on the left-hand side. All right, that's the way you do it. So who can tell me in the chat if that's our function, or that's our function, what is f of 0? Who can tell me? Smash that chat button. What is f of 0? Who can tell me? There's 12 people here. Okay? Who can tell me what is f of 0? It's 0. Yes, it's not a trick question. So this is 0. So it's basically this, right? That disappears, and I'm left with this. Okay? All right. So what is f of x? Well, it's that. Divide it by x. So let's work out the derivative. So the derivative is going to be, well, this goes to 0. This is a half, right? And if this goes to this, and I put in x equals c. Okay, so what I'm going to do is show that this is positive, and therefore this is positive. This is positive, so the top bit has to be positive. Okay, so now you know this part is positive because this thing down the bottom is always greater than 2. Right? So you got half minus something that's not quite as big as a half. Okay. So what do we know if this is positive? Well, the bottom bit's positive, the top bit has to be positive. Okay. That's it. Bum, 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 bum. This inequality is exactly the same as this inequality. Okay. Okay, I differentiated. This is the derivative here. Okay, so this bit goes to this. All right, so I differentiated this part, got this, and replaced x with c, right? See how that's c? So you differentiate this with respect to x, and you replace x with the letter c. Okay? Yeah, good. All right, that's a good question. So to show the other half, you just repeat the process, but you get a different f, obviously. Okay. So if I wanted to say do this one, it's pretty much the same thing, right? Okay, I'm not going to repeat that. I mean, it's pretty, it's just exactly the same steps. All right. Okay, let's do an error bound. Oops. Let's do an error bound question. Okay. So there's the discussion in the text. Let me go back to the actual questions. Go, 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 go. Okay. So there is a video one for this one, but it's a special request. Use the mean value theorem to find an upper bound for the error involved in the following. Okay. So let's have a look at how we do it. The nice thing about these questions is they're all the same. The strategy and the solution methods are really similar. So I thought I could do this and then we can switch to some algebra. Okay. All right. So root 17, quite hard to calculate by hand, but root 16 is an approximation, and we know that root 16 is 4. So how well does 4 approximate the square root of 17? That's pretty much what it's asking you. Okay. And this upper bound on the error. So let's have a look at that and see how we go. All right. So back to our document camera. So what I'm going to do is I'm going to let f of x be the square root function. In this example, we're looking at the square roots of numbers. And this is going to be our interval of interest. We want to get the square root of, or approximate the square root of 17, and we know the square root of 16. So this is a good interval to play on. Okay, so does this function satisfy the conditions of the MVT? Who can tell me? Does f satisfy the conditions of the MVT? The mean value theorem? Who can tell me on the chat? Does this function yes, it does, Oliver and Kevin, because it's continuous on this closed interval. Thank you, Eloisa. So by MVT, you know me. Okay. So what we can do now is, if we wanted to, well, I mean, this is just 1, so it's going to be pretty easy. So let's think about this. Okay, so that disappears to 1. And to work out this error here, so this is like the difference between the true value of root 17 and the square root of 16. It's all about getting an estimate on that, right? So root 17 minus root 16 is going to be, all right, let's differentiate this and put in x equals c. Okay, so the difference between that and that is all about this now. Okay, and what do you know about c? Well, c is between 16 and 17, right? So 1 on 2 root c is going to look like this. Okay, it's a decreasing function, and therefore it's got to be less than whatever the value is at the left-hand endpoint. Okay, So what's that? That's 16. So this is going to be less than 1 on 2 root 16. So that's easy to calculate now. That is just 1 on 8. So what is an upper bound on the error? It's 1/8. Okay, so this is usually the case. You apply the MVT, you could compute the derivative, and you form some inequality on the derivative on the interval of interest. Okay, that's the idea. So we know that, well, 4 is an okay approximation to root 17, and it's going to be out by no more than 1/8. Okay, so that's the way I look at these problems. So with the other kinds of questions, they're very, very similar, right? So let me just go back to my PDF and I'll show you. So what kind of function would we be looking at for this second question? Who can tell me in the chat? In the first question, we looked at the square root function. What do you think the function would be for this particular question? Who can tell me in the chat? Yeah, the squared function. Great job, Oliver. Eloisa. And what about part C? What would the function be in part C? Who can tell me? Who can tell me? That's right, 1 over x. Exactly. Kevin, I think you mean 1 over x, right? Yep. So yeah, so these are very standard problems. Okay. That's all right. So what about some algebra? What about some algebra? So I thought we could do maybe one question from vectors and maybe a few questions from complex numbers. Okay, but let me know what you want to do. Let me just get my notes here. Yeah, 28 is a nice question in my opinion because it asks you to do lots of different things. Okay, so I thought we could do 28, even though it's a routine one. There aren't any hard ones for this part, so I thought we could just do this one. So you've got 4 points with these coordinate vectors. Find the parametric form of a plane that goes through A and is parallel to these, I guess these vectors, you could call them vectors or lines. Find a vector normal to the plane and use the point normal form to find a Cartesian. So there's 3 parts to this question. Let's work it out. Okay. So let me go back to my dock camera and we can make some notes. All right. So this is 28. Okay, so let's introduce our 4 points. So O is just going to be the origin. A is going to be this. B is going to be this. And C is going to be that. All right, so given those 4 points, they're asking us to find the parametric vector form of the plane. So PVF, parametric vector form of the plane through A and parallel to OB and OC. Okay, so it's pretty easy to do that. These are just position vectors. We can basically just write down the PVF straight away. Okay, so this is a pretty easy question, or at least an easy part. So it's OA plus lambda 1 OB plus lambda 2 OC, and I'm going to put my lambda 1 and lambda 2 as my parameters. So OA is going to be this written as a column. OB is just this written as a column. And OC is this written as a column. Okay? Yeah, pretty easy, pretty easy. Okay, so find a normal. So the next one is compute normal n to pi. Okay, so we want a normal vector to the plane here. Can anyone tell me on that chat, smash that chat button, how can we compute a normal vector from part A? Who can tell me? Who can tell me? Come on, don't be shy. Oh, Kevin, cross product. What things would be? You're absolutely correct. What things would be crossed together? What might we do? Tell me about it. What would the things that we cross together? What would they be? What would the two vectors be? Yes. OB and OC. Great. All right. Great job, people. I'm looking at the chat. Does it matter which order? Could it be OC cross OB? Would that still work? Who can tell me yes or no? It still would work. We don't care which normal it is. It can be either one, right? Great job, Eloisa. So let's, yeah, great job, Menglu. We can use any order we like for this one. Obviously, the answers would be different by a minus sign. Okay, so OB, 1, 0, -1, OC, 2, -1, -1. Okay, so the way that I like to do these, I start up here, I expand along the top row, and you cover the first row in the top column, and you compute the determinant. Then you move over here, you compute that and the determinant of what's left. And then you move over here, you cover that, and you compute the determinant of what's left. Okay? You may do it in different ways, but that's the way that I like to do it. Okay? So it's going to be I times the determinant of this. So that's 0, and that's going to be -1. Okay? J's there, so that's going to be that times that minus that times that. So -1 plus 2, and you've got a negative sign. So I think it's going to be -1 plus 2, which is +1, but you've got the negative sign. And finally, okay, that times that minus that times that, well, that's 0. So it's going to be -1. Okay. All right, so that looks like a normal vector to me. So you can write it like this, of course, as a column if you want to. All right, The last part of this question is, whoops, it's about use the point normal form to find a Cartesian equation for the plane. Okay, so let's look at point normal form and explore that, and then we can move on to some complex numbers. Okay, all right, so the point normal form, PNF, is something like this. Sorry. Okay, so n is a normal vector to the plane, x is the position vector of a point on the plane, and a is a given point on the plane. Okay, so here we've already got our normal vector. A could be that point, or it could be that point, right? Let's take this point just to make it a bit more interesting. Oh yeah, no, it's this point. It's this point. Okay, so let's consider -1, -1, dotted with x minus a. So x minus 1, y minus 2, z minus 4. So all you do now is expand this and you get the Cartesian form. Okay, so let's see if I can squish that in. So it's going to be -1 times that. So let's just move that over here. So I'll put the 0 sign on the left hand side. So all you've got to do now is simplify this. Excuse me. Okay, so -x minus y minus z. Okay, 1 plus 2 plus 4. So I think that should be your answer. Okay, that equals 0. That is your Cartesian form. Okay, so you can see the point normal form is great because it easily gets you from PVF to the Cartesian. Yeah, so that's pretty cool. That is pretty cool. What do you think? Yeah, it's pretty cool, bro. I love it. Okay. Okay, so let's move on to complex numbers. Now, don't let the name complex numbers worry you, okay? Complex numbers are designed to make things simple. Okay, so people see the name complex or the word complex and they go, oh my goodness, that sounds so complicated. No, the idea is to simplify the mathematics, which is really great. Okay, so let's have a look at some of the questions. All right. So I think 2, 3, and 4 are interesting. And then we can do some more other questions, okay? So who can tell me, for these sets of this set of numbers, right, 0 to 9, is it closed under addition? Okay, so what does closed under addition mean? Can anyone tell me in the chat or on your microphone, what does it mean for a set of numbers to be closed under addition? Who can tell me? Who can tell me? What does this mean? Let me know on that chat. Smash that chat button. Or let me know if you turn your microphone on. What does it mean for a set of numbers to be closed? Oliver's on the chat. If you add any two numbers in the set, the result will still be part of the set. Okay, great, Oliver. Thumbs up, buddy. So, is this set closed under addition? And what do they mean by proving your answer? So the first question is the set closed under addition? Yes or no? And then they ask you to prove the answer. So who can tell me? Is it closed or not? Is it closed? Who can tell me? Eloisa says no. Anyone else want to say something? There's 16 people here. Some people are being very quiet. Kevin says no. Shakira, what do you think? Do you think it's closed under addition? Let me know in the chat. Shakira, let me know. Do you think it's closed under addition? Shakira, hello? Are you there? Let me know if you're there. Correct. Excellent. Thanks for piping up in the chat. So you are correct. It's definitely not closed under addition. But how do we prove it? How do we prove something that's not like it's not closed? Does anybody have an idea how we can prove it? Ah, Naomi, yes. Great suggestion, Naomi. Yeah, Maximilian, obviously that's a good suggestion, same as Naomi's. Naomi's given a counterexample. Okay, so what Naomi's done here is she said, right, I'm going to find a pair of points that break the closed axiom, right, or condition, and she's taken 9 and 1. Okay, so if you look at 9 and 1, you add them together, they're not in the set. So that's called a counter example. Okay, so let's run with that. Okay, so we want to put together what's known as a counter example. So choose 1 and 9 and consider 1 plus 9. That's 10 and it's not in the set S. Okay, so this is this is similar to what you're saying, Maximilian. But you can also see that, I mean, 0 and 1, if you add them together, obviously you still get 1, which is in the set. So yeah, so you're both correct. Thus, we would make a conclusion. This is not closed. Oops. Under addition. Okay. So there's a counterexample. All right, what about the second part of this question? Okay, so let me just go back. I'll come back to the document camera in a second. Can any finite set of integers be closed under addition? Now, this is a great question because it's not clear whether this is true or not, and it's also, what do they mean by any? It's not clear. Okay, so on the chat, can anyone give me an example of a set of numbers like this one that's finite and that it's closed under addition? Who can give me a simple example of a set of integers, a set of whole numbers that is closed under addition? Who can give me a list of numbers or a set of numbers? Who can do it? Come on, don't be shy. Don't be shy. Oh, Eloisa. Oh, Oliver. Maximilian. Loving the combination so far. Anybody got anything to add to those sets? I guess it depends what they mean by the set of integers as well. Do you? Oh yeah, integers, whole numbers. That's fine. That's fine. So any other variations? Yes, Oliver, you can add a number to itself. So Maximilian's looks good. Oliver's looks good. Eloisa, not sure about yours because 2 plus 2 is not in your set. Yeah. And Maximilian, 1 plus 1 is not in your set. Okay. So Oliver, I think yours is pretty good. Right? So because 0 plus 0 is definitely 0. So that's fine. So let's use your examples there. And
Mom, I just realized that we forgot to do my clarinet lessons. I'm really sorry for forgetting.
can you guys hear that? That's my son. Hey Google, broadcast.
What's the message?
I'm having a lecture. I don't need to hear your clarinet stuff.
Okay, broadcasting now.
Okay, so back to the program. So consider the set. I don't know. Let's call it H. Oh, actually, let's call it S. No, O for Oliver. Okay, I'll put a little hat over there, right? Actually, I'll put a hat like that. That's my funny way of making that different from that. Okay. This is closed under addition. Okay, so it is possible to generate a finite set of integers where they're closed under addition. Okay, since 0 plus 0 equals 0, which is in the Oliver hat set. Nice. All right, let's move on to part 4, and then we can do some complex numbers. Okay. All right, so this one. Is the set closed on multiplication and division? Okay. So what do you think in the chat? Is it closed under multiplication and division? Louisa says yes. Anyone else want to challenge that? Paranita, what do you think? Do you think it's closed under multiplication and division? Let me know in the chat. Paranita, let me know if you're out there. Is it closed under multiplication and division? What do you think? What do you think? Naomi says yes also. Paranita, what do you think? Do you agree with Naomi and Eloisa? Show me a sign if you're out there. Let me know in the chat. Do you think that this is closed under multiplication and division? Paranita, are you there? Paranita, hello. Come on in. Let us know that you're there. Okay, I'm not sure what's happened to Paranita, but Naomi and Eloisa are correct. So let's have a look at this on our let's call this, I don't know, let's call it P for Paranita. It is closed under multiplication and division. Why? Because if you multiply this with itself or this with that, you either get +1 or -1. Okay? So, I don't know, let's just sort of just simplifying this. That's it. Okay. I mean, if you, yeah, that's fine. Oh, all right. Simple structures, but they're important because they give sort of the theoretical basis that we know what we're doing with different number systems. So let's jump to something a little bit more complex numbery. Okay. And I thought 17 was an interesting question. Okay, so this will be the last question we do. It looks hard, but actually it's not too difficult once you know what to do. I think the hard part with this question is getting started. So let's spend a couple of minutes doing this one, and then we can finish the lesson. Use the properties of the complex conjugate to show that if you have a complex number alpha, that's a root of the quadratic equation, and the coefficients are real, then so is the conjugate of alpha. Okay, so basically alpha and its conjugate satisfy this polynomial with real coefficients. Okay, so let's do that, and we can work out what's going on. It's a pretty interesting result, I've got to say. All right, so consider the following. Where A, B, and C are real numbers. And we're going to let alpha be a complex number that satisfies star. What this question asks us to do, and let's say it's a complex number. Okay, so this funny looking C just means the set of complex numbers. We want to show that this also satisfies the original equation. Okay. All right. So remember with the conjugates, if you have something like, I don't know, alpha equals 3 plus 5i, then the conjugate is just 3 minus 5i. So you just change the sign on the coefficient of the I here. All right. So how do we do it? Well, let's consider the following. The proof basically lies on the properties of the conjugate. So we know alpha satisfies this, so we replace x with alpha. And let's take the conjugate of both sides. So this is my super conjugate line. Okay, the super conjugate. Now, who can tell me what is the conjugate of 0? Who can tell me in the chat? What is the conjugate of 0? It's not a trick question. What is the conjugate? Eloisa, yes, you are correct. Okay, so that is 0. And I can break these things up into parts. Okay, the conjugate is like a linear thing where you can break things up. Okay, so if I take the conjugate of this, I can move it inside the squared sign. Okay, the conjugate of a real number is just itself. You can break this up into 2 bits. The conjugate of B is just itself. The conjugate of A is just itself. Why? Because they're real numbers. Okay, so what does this tell you? It tells you that the conjugate must satisfy star. Okay. So that wasn't too hard at all. So the next part of the question, and this is the last one I'll do. If this satisfies an equation like this, then, so here we've just got a 1 instead of a and B and C are real. What's another solution? Just from what we've seen in part A, who can tell me, without doing any calculation, what is another solution to this problem? Who can tell me? Don't be shy. Yes, Eloisa, you're on fire today. You are rocking it. The conjugate of this, right? So what does it tell you? It tells you if you can find one solution, you get the other one for free. For free, I tells you, for free. Okay. So that's one of the really nice things about these complex number type solutions. If you know one solution, you get the second solution for free. Okay. Exactly, Elisa. I don't know where everyone else is. I'm going to put up. Are you awake? All right. It's 16 people here. I'm putting out. Someone's put no. I don't know how you can answer no when you're not awake. Exactly. Eloisa, you and Naomi and Oliver and Maximilian, you're just carrying it. You're the whole show today. Yep. You're the whole of the tutorial. Anyway, who hasn't responded? Oh, Paranita, you haven't responded. Kevin, Junsheng, Aichen, why you not respond to the poll? Why you not respond? Oh, someone's responded. Too much information, Kevin. That's hilarious. All right. Okay. I will show the responses. All right, folks, that is enough for today. So let me kill the recording.